Okay, so this question seems to be very easy, and I'm going to explain it very quick in case that you have a question, and I'm going to, in case that you need a longer explanation, I will add that. I will add a longer explanation. So here, in principle, this seems to be very easy. Suppose that the mating of this monohybrid cross between these two heterozygous, and when you cross these two lines, where there is a that is recessive allele produce 8 of spring, what is the probability that the ratio of dominant to recessive of the offspring is equal 1 to 1? So if you go to the textbook, there is a very similar exercise. And the idea is that you have to apply this formula. Here you don't have to use the multiplication rule. You don't have to use the addition rule. In this case, you have to apply this binomial theorem. And these, you have eight trials. You have the probabilities. These are the number of dominants. So 8, so 4, and it's 50-50, so it will be 4, 4, and the probabilities of dominant, as this is a heterozygous, 3 out of 4 will be dominant, and 1 out of 4 will be recessive. So you replace this in the equation, and you get this. So less than 10% that you get that you get the probability that they are asking. So if you understand that, and you have to stop watching the video, and maybe that was pretty easy. In case that you have a doubt, I'm going to explain it in a much slower way. Okay, so remember, you have to apply this formula. Okay, so now we're going to talk about all this problem in a much slower way, in more detail, and we have talked about addition rule, multiplication rule in the previous video lectures. Now we're going to talk also about combination and permutation. And in all these cases, we are counting objects in different ways. So remember, in the addition rule, you have mutually exclusive events, and or this word is very important. So for example, what are the chances to get in a head or a tail if you flip the coin 3 times, 100 times? Yeah, there is a formula for that, and we can also apply genetics into that. Independent events, so when you have a multiplication rule, is the same thing. What are, if you are flipping a coin 100 times, what is the chances that you get a head and 3 tails? Yeah, so here, if you flip the coins here 100 times, what are the chances of getting this? So again, in this case, well, this one were mutually exclusive, you use the word or. Here they're independent, and you use this word and. Not always, but if this could be an indication that this is a multiplication rule. On the other hand, when you have these two, combination and permutation, these are dependent events. So what happened in the past determine what happened in the future. Yeah. So let me show you an example. Here you have two types that are the no sequence, and that there is no sequence of events, that it can be disorganized, and you have the permutation, that they will be sequence of events that the order is important. So in other words, imagine what we are doing with combination and permutation is you are arranging objects. Yeah, so they are asking you, for example, uh, with a combination is, what are the chances that you get 2 blue balls, 1 green, and 1 red one? Yeah, so 2 blue balls, 1 green, and 1 red one. Yeah, but here they can be 2 blue, 1 green, and 1 red, or it can be 1 red, 2 blue, or 1 green. Yeah, so the order here, and you can have many more options. Yeah, you can have even 1 blue, 1 green, 1 red, and 1 blue. So you can have many different ways to organize it, so you have many more options. the sequence of event is that it should be an order that you should get first this one, later this one, and later this one. Okay, so again, we have to summarize this. You have to remember there is 4 options, and each one is different. Once there is dependence, and in the other one there is no dependence. Yeah, for example, when you're flipping a coin, what happened in the past? Every time when you flip again the coin, you have a new event, and the probability start again. Here in the combination and permutation, when you remove one of these balls, now you have a different probability. Okay, so now let's apply this into genetics. So in the addition rule, as we talked before, similar to flipping the coin, remember for example, the formation of gametes. It looks very similar to flipping a coin when you have this case when you have 2 alleles, that one is homozygous and the other recessive. So as you watching the video before, for example, the probability of getting a heterozygous is 1/4 and 1/4. So here you see the probability. Yeah, so it's 1/4, so it's half, and the probability of getting a homozygous here, it will be also 1/4. Here's here and here. Okay, so pretty easy with the multiplication rule. Again, independent events. Again, very similar to flipping a coin. For example, this is a typical exercise that we use in genetics. What is the probability of getting 3 girls in a row? So the probability is half of the chances. So the first time is 50%, then the second time 30%, 50%, the second time 50%. When you multiply all of them, is 1 out of 8. Okay, so multiplication rule and addition rule. And as we explained before, there is also these 2 examples, very easy. Okay, now I want that you read this exercise and try to solve it. Okay, try to read it, try to solve it. You say, is this addition? Is this multiplication rule? How do you know that? There is any clue that can help you to solve this exercise? Okay, so let's try. They are saying that you have 4 girls. Here you have these 4 girls. Then there is 1 boy, and then there is a girl. And remember, every time you have the same chances that when you have a kid, that you have half of the chances of getting a girl, half of the chances of getting a boy. So these events are independent, and here as a proof of that you have this and. Okay, so this is definitely a multiplication rule. So they will be for 6 independent events, and it's pretty easy. 1 out of 64. Yeah, all these are the girls, and this here is the boy, and here are the last girl. Pretty easy. Now I want that you solve this. Okay, now I want that you read this if you want, and you can stop the video. And one clue, look what happened here. Okay, so 10 seconds and try to think how to solve this exercise. So if you see here, they're asking you again, they're asking you a probability, but in this case, again, 6 children, so it looks very similar. And here you have again 5 girls and 1 boy, but they are not giving you a specific order. Yeah, they are saying to you, we have, this could be one, the order could be this one, or can be this one, or can be this one, or can be this one. So here you will have this look like you can calculate the probability for this one, 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 and for this one, and then you will have to add it together. Yeah, so this could be a fusion between the 2 of them, and you can do all those things, or you can just do fuse them into one formula. Okay, so let me show you. So instead of that, of the multiplication rule, here you're using the two rules, and this is called the binomial theorem, and you can see that in your textbook if you have any doubt. So here, in this case, you have an order event, and you are combining this probability of the rule 1 and 2, and this will be considered like a rule 3, and here is the formula that is from that you can find it in your textbook. And let me here here is the number of trials. Here you have the probability of one event, the time that one event happened, the time that the other event happened, and here is the probability of one event and probability of other events. Okay, that sounds very confusing. So let's continue with the exercise in a second, and you will see that it is much easier. So just one thing to remind you to go into this. There is this symbol, there is the factorial. Yeah, so here, just to remember you, if you have 7 factorial, it's like 7 multiplied by 6, by 4, by blah, 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 blah. And remember, when you have 0 factorial, it will be equal to 1, okay? So now that we know that in case that you have a doubt in there, that information you needed to solve the exercise. So now we are going to see again this exercise, and that it looks so complicated and it would be much easier. So, and remember, there are two things that you need to remember. We assume that the probability of having either a boy or a girl, a son or a daughter, will be half. And remember that here the order is not specified, so we can use the binomial theory, okay? So we have this formula that in the beginning looks too complicated, but I will show you that it's very easy to interpret. So here they're asking you for this n, okay? And this n is the number of trials. So here the number of trials is very easy. It will be 6. Why? Because there are 6 children. So you have to repeat this 6 times. Okay, the second one, super easy. I'm going to put it in black. The number of girls is 5. Yeah, so this one here, it will be 5 factorial because they told you there are 5 girls. And then they ask you for t, very easy. And t is the number of boys. So they told you 1 boy, so this is why we put 1 boy here. And later they ask you for this probability of a boy or probability of a girl. In this case, it's very similar. So let me put it with purple, sorry. So with purple. Some cases it could be different. In this case, the probability of having a boy or of having a girl, a daughter, it will be the same. And I already told you that is here. You know, it's half. So this is why we have half here. So now we just have to replace all these numbers in the formula, and you're going to get this. Yeah, so we have 6 trials, 5 girls, 1 boy. The probability of a boy is half, and you multiply the raised to the power of 5. The probability of a girl raised to the power of 1 because you only want to have 1. And then we solve that, and what we get is this 3. There is 3 out of 32. Okay, so going back to these two exercises, so remember here you have only one way to do this. Yeah, now in this case you have 6 different ways to do this. So here you have the probability will be 1 out of 64. Here on the other hand, if you see, your probability is 3 out of 32, or if you go before here, it will be 6 out of 64. So because you have 1, 2, and blah, 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 up to 6 different ways to do the same thing. Okay, so this probability is much higher, yeah, than this one in this kind of exercise that make a lot of sense. Again, you could have done this exercise by having multiplication rule and then adding, and all of this one will give you again the same result, 1 out of 64, and then you add it 6 times, so you get 6 out of 64. So it's just for this case it will be relatively easy. However, for exercises it will be much easier to use the formula. Okay, so now this is an exercise that I want that you try to start trying to solve it. I will give you 5 seconds to read it. If you want, you can stop the video, and the first thing that they give you is already tell you what type of statistical tools you need to use. And maybe you can start using a paper and try to see all the different probabilities that you need to, all the parameters that you need to collect. Okay, so I will stop talking and you can give a read. Okay, so now if you want to keep solving it, stop the video. If not, I will tell you more information. So here there are key things for this. So you need to know that there are 2 heterozygous, because this will tell you the probability of a dominant and recessive. So here you are 1 heterozygote, the other heterozygote here, and from this one you can get the probability of being dominant. Yeah, look, all these dominants, and here you have only 1 recessive here. Okay, that is important. But let's look what else you need to know. So here they also give you these very important 8 children. So this here is they give you the number of trials. They are telling you the probability of having 6 of them will be dominant. So this will be 1 variable. And here they give you the other 2 will be recessive. Okay, so they give you already all the information. So this that looks so complicated is actually really easy. So let's try to solve it together. So first thing, the probabilities. As I said before, super easy. The probability Q, that is that a child shows a recessive trait. Here, only 1 out of 4. The probability of a dominant trait. So here you have 1, 2, and 3 out of 4. So 3 out of 4. So you have already two variables that you need to for the formula. Let's go on, continue with the other ones. So here, as I said before, here the number of trials is 8. So here you already got this one. Also they told you that there are 6 children. So here you have your S here. They told you that 2 of them will be recessive. So here you have this T here. And these 2 that I'm going to put in purple, we already collected before. And I explained it to you how to do it. So now let's put everything in the formula and you will get this. Yeah. And remember, 6 come from, from 6 children. Here the 2 will come from these 2 from here. Okay. So now you start solving the equation and you're going to get this probability that is 0.3. So in other words, there is only 30%, 31% of the families with 8 children will experience the 3-to-1 phenotypic ratio. Okay, so it looks very difficult, but it was actually pretty easy and we were able to solve it. In class, one of the students or I will solve this exercise. Please start thinking about it.